Good morning everyone, and welcome to today's worked exam answer video. Today I am having a look at an A-level AQA question whereby we are reacting an acyl chloride with a primary amine, and we have to name the mechanism, outline the mechanism and name the organic product. So this would come under one of two topics. We've got either carboxylic acid and ester derivatives, of which an acyl chloride, is one of those, or this could also be connected to the amines topic because we're using a primary amine as our nucleophile, and the reactions of amines as nucleophiles is something that's covered in that topic as well. Either way, there's only one mechanism that we would be drawing in this instance. I'm going to outline that and be really clear on where your marks are going to come from and what you should and should not be doing. As I've mentioned before, I believe in these videos the examiners are really picky with mechanisms in terms of where and how the curly arrows are drawn, so I will make sure that I am clear with mine and I explain clearly what is expected. And yeah, let's get going. So there were some earlier parts to this question that were looking at amide links being formed when amino acids were being joined together. I decided just to focus on this mechanism for this particular video, but I can have a look at the formation of a dipeptide from amino acids in another video. If anybody's keen for that, please let me know. So that's why the first bit says an amide link is also formed. So for us, the key thing is that it's an amide link, and that is formed when an acyl chloride reacts with a primary amine. And the three things we have to do: name, 1, outline the mechanism, 2. For the reaction between, that is propanoyl chloride, CH3CH2COCl, and that amine there is ethyl amine. So we've got to name the mechanism for 1, outline the mechanism, which is going to be worth 4 marks, and then we've got to give the IUPAC name of the organic product. There will be 2 products in this reaction, one of them will not be organic. They want us to name the organic one. I will include the other one in the mechanism and explain how that forms, but like I say, we only have to name the organic one. So when it comes to our mechanisms, and again I believe I've said this before, we need to be able to recall really quickly what mechanism is involved in the reactions between different homologous series. So as soon as we see that we're starting with an acyl chloride, we should be thinking one of 2 things. One is what we need to be thinking about here, which is nucleophilic addition-elimination, and that is the answer here because, as I said, the amine is acting as the nucleophile. The other mechanism that we may be considering with an acyl chloride is electrophilic substitution. Reactions of benzene can be either nitration or Friedel-Crafts acylation, and for the latter we would use an acyl chloride in the generation of the electrophile, so that's the other one where we need to be able to make that connection. But because we're following up our acyl chloride with a very good nucleophile, this mechanism is going to be nucleophilic addition-elimination. Now, it might be that you can't remember the name of the mechanism, but you remember how to draw it. My advice is that we understand mechanisms well enough that we can either, from the mechanism we've drawn, figure out what the name is going to be, or vice versa. If we can remember the name but we don't quite remember where the curly arrows go, again, understanding what these words mean can help us to piece together the mechanism should we forget where some of those curly arrows should go. So the first thing that I'm going to do here is I'm going to draw out the structure of the acyl chloride, the propanoyl chloride, and I'm going to do that as follows. I'm not going to draw out the carbon and hydrogen bonds because they're not going to be involved in the mechanism. Now I know that because nucleophiles are electron pair donors and they want to be attacking something that has a positive or a partially positive charge, which is going to be this carbon here, because it is a part of this polar C double bond O carbonyl group. It's also attached to a chlorine, and chlorine is more electronegative than carbon. So that's where we're going to be attacking with our nucleophile. Again, I don't need to draw out the CH3, CH2 of my nucleophile because it is the nitrogen that has the lone pair of electrons that can be donated in this first step. So the first two curly arrows we need to draw are going to be in this step, and this is where the addition part of the nucleophilic addition-elimination mechanism is going to occur. So curly arrows have to start at one of two places, a lone pair of electrons or a covalent bond. And that is because any curly arrow we draw shows the movement of a pair of electrons. So by drawing my first curly arrow like that, I'm showing that this pair of electrons here is going to form a bond between the nitrogen in the nucleophile and this carbon here. Now if we do that, the carbon would be forming 5 bonds and carbon only wants to be forming 4 bonds. Therefore, we need to break a bond. Now some students would want to get rid of the chlorine straight away. If we were to do that, that would be nucleophilic substitution, not addition-elimination. We can't break the carbon-carbon bond this side. The only way we can add without taking anything off in this first step is to open up the carbon-oxygen double bond so it becomes a single bond, and that means that we're not losing any atoms in this first step, we're just adding the nucleophile on, which is exactly what we need to do. Now we need to draw what the intermediate structure is going to look like. So the CH3CH2 is unchanged. Then we now have a C single bond to the oxygen up there, which it's gained both electrons from that bond that was broken, one of which was its originally, but one of those 2 electrons will have belonged to carbon. So it's now got 1 extra electron than it did. And I'm also going to pop a lone pair on there, and you'll see why in a second. The chlorine is still attached at this point, and now the nucleophile is added on. So we have the nitrogen bonded to the carbon, as shown by that first curly arrow, the 2 hydrogens of the NH2, and then we've got the CH2, CH3. Nitrogen, because it's using its lone pair now in a bond, doesn't have sole control of the lone pair, is how I like to describe it. So it's relatively electron deficient, so we're going to have a positive charge on our nitrogen there. That intermediate gets you 1 mark. Each of these curly arrows gets you 1 mark. So for the mechanism alone, we're now on to 3 marks. It's going to be 1 for the name of the mechanism, 1 for the name of the product, and interestingly and unusually, but I do think I know why, we're only going to get 1 mark for the remaining 3 curly arrows that we need to draw. And I think that is because we could not be looking to get 7 marks or 8 marks for this question, but 7 marks for a name and outline a mechanism question. So in order to eliminate the chlorine, which is what we want to be doing here, we are going to reform the double bond. We are going to then be able to eliminate the chlorine, and we need to sort out this problem at the bottom. We need to give the nitrogen its lone pair of electrons back, and we do that by breaking one of the nitrogen-hydrogen bonds, and both the electrons in that bond go towards the nitrogen and the hydrogen leaves with none. Now in terms of kind of knowing about the curly arrows in this step, it also helps if we know that when we're doing nucleophilic addition-elimination, we're doing an acylation reaction, and in an acylation reaction we are changing what atom or group of atoms appears next to the C double bond O. So we know we're going to have to reform the C double bond O. We know the chlorine's got to go, and then the nucleophile minus a hydrogen is going to be now what appears next to the C double bond O. That's what acylation reactions do. In terms of the mechanism now, you don't need to draw the final product. There is only one possible product we can make in this mechanism. You're not going to get a mark for drawing the product. However, in this case, we have to name the organic product. So it may be that you wish to draw the product to make it easier to name. I will draw it here, but I want to make it really clear that you don't have to draw the product if there is only one product that can be made. In some mechanisms, like electrophilic addition and some elimination mechanisms, we can get multiple products. And in those cases, whichever mechanism you draw, always draw the product that would be formed from your mechanism. But in the others, including this one, where there's only one product we can get, drawing the product is not essential. It's not required, you don't get marks for it. But if you draw it, but you draw it incorrectly, you will lose one of the marks that you have gained for doing something correct in the question. So I won't say don't do it, because I used to do it myself because I didn't feel mechanisms were finished unless the product was drawn. I'm a bit wiser now and a bit less stubborn perhaps. If you are going to draw the product, just please be careful and aware of the risks. So I will draw the product here so that we can then name it together. So again, CH3, CH2 is not changed. We've now got the C double bond O back, and then in the position next to the C double bond O, we've now got a nitrogen, which has lost one of its hydrogens, but it's still got one, and then it's got the CH2, CH3. The other product that we're going to get is formed from the two atoms that leave in this step. So this hydrogen is leaving as a H plus ion because the electron that it had, that it shared with the nitrogen, has gone to the nitrogen. So this leaves as a H plus. This leaves as a Cl minus ion because that gets both electrons from that bond. H plus and Cl minus make HCl. And when we have any acyl chloride reaction, any acylation reaction involving an acyl chloride, HCl will always be made as the second product. Now that is not an organic product because it doesn't contain carbon, so it's this hideous looking thing that we're having to name. Now they did give us a bit of a clue that we were forming an amide link. So first of all, let's make sure we're happy with what the amide link is. It is the C double bond O, and on that same carbon having an NH, like that. Now an amide itself can either be an NH2 here, or this is actually an N substituted amide because one of the hydrogens on the nitrogen has been substituted for an alkyl group. They would both be amides. This is what an amide link would be because we need to be able to carry on kind of after the amide linkage. So we'll see these in polyamides. We see these links when we join amino acids together, although we'll probably call them peptide links or peptide bonds in that instance. But yeah, that's our amide link. So when we are naming any type of amide, whether it's a normal amide or an N substituted amide like I have here, the ending of the name is always going to be amide, which is quite nice, and the number of carbons here, including the C of the double bond O, will be the prefix for that amide. So this is going to end with propanamide. The difference here, because it's an N substituted amide, is we have to indicate that we have this group on the nitrogen, and that's why I call them, not just me, but I definitely refer to them as N substituted amides, because we say what is on the N that has substituted the hydrogen. So the name of this product is going to be N, and then this, which is an ethyl group. So that's going to be my prefix, if you will, and then 1, 2, 3, propan amide. If that was just a hydrogen, it would be propanamide. Because we've switched the hydrogen for this N ethyl, propanamide is the name of this particular organic product. So when we're drawing our mechanism, please be really careful with your curly arrows. Please draw your bonds nice and long so you can show that the arrows are coming from the bonds. Please make sure that you have them pointing at atoms, or lone pair curly arrows pointing at bonds or atoms. Don't draw things really small. Make things a little bit bigger. Have nice long bonds so that it's really clear what you are showing with your curly arrows. Try and think about placement of charges. So here, this positive charge, I could have put it there, but then that would have made this curly arrow really squidged. So I chose to put the positive charge on this side with the alkyl group because I knew that wasn't going to be the bond that I was going to be breaking. Again, make your lone pairs really clear, because if you draw a curly arrow that doesn't start from a lone pair, then you won't be getting the mark for the curly arrow. So make your lone pair on your nucleophile clear, make the lone pair on this oxygen atom clear. Use all of the space that you've got. You don't need to be squishing it up, okay? That's what they're going to be looking for in particular with this mechanism, and as I said before, the charge on this oxygen atom being negative and the charge on the nitrogen of your nucleophile, once it's added on, being positive. That's what they're going to be looking out for here. If that's generated any questions, as always, please leave me a comment on the video or send me an email to missgtutoringandresources@outlook.com, and I will be more than happy to help. If anybody's got any similar questions they want me to have a look at, again, please let me know. Or if you have any question requests that you'd want me to have a look at, again, please just get in touch. Thanks so much for watching, guys. Take care.